Everybody's favorite, conjugate addition again. So, as a recap, remember that when we're looking at conjugate addition, we're referencing the polar pi bond being one bond away from a non-polar pi bond. So it is that conjugation that allows for two potential electrophilic sites. Okay, you get the electrophilic site at the bottom and the electrophilic site where the carbonyl is located. And deciding which one you attack or you react with your nucleophile is all dependent on the strength of the nucleophile. So there are some that add reversibly, and if they add reversibly, what will happen is that they will first attack the most electrophilic site, which is the carbonyl carbon. They will go through and make that kinetic product. But because they add reversibly, that reaction will revert back to starting materials. Okay? Some small percentage will clear the activation barrier to go to the thermodynamic, but the thermodynamic is now irreversible because it is lower in energy, which means proportionally you see a massive shift towards the thermodynamic product coming out of it. If, however, your reaction is irreversible, what that says is that the activation barrier between our reactants, or sorry, the delta G is the word I'm looking for, between our reactants and our products for the kinetic is now so large that when we go through to form that fastest product, I cannot reverse the reaction. Okay? So nucleophiles that add irreversibly will go through, form the kinetic, but now they can't revert back, which means anything that is moved across to the kinetic stays as kinetic product. Anything that moves to thermodynamic will also stay as thermodynamic, but usually if you're running under these conditions, you're running with lower temperatures, which means very few molecules ever clear the activation barrier to clear to the thermodynamic product. And so the preference that you get is just the kinetic. So it all comes back to that, defining that difference between reversible and irreversible. And remember what we talked about in those past videos was talking about our reversible nucleophiles being oxygen, nitrogen, and our halogens, because those could all stabilize the negative charge relatively well. The irreversible ones were all carbons and hydrogens, because carbon and hydrogen can't stabilize that electron or the electrons of that negative charge very well because they're small and low in electronegativity. There were some kind of exceptions. Okay, whoops, because that one is an oxygen, we could include that one. We talked about cyanide being an exception, the Gilman reagent being an exception, and one that we didn't actually explicitly talk about is here at the bottom. And what you should notice here is that if we did a little arrow pushing on that, that should stand out because what that is an enolate. The enolate is also on that threshold between reversible and irreversible, which means if we bring it into a conjugate addition type system, reactions get complicated and we now need to evaluate that process. Okay? The enolate is actually a step kind of more in that line because we're oscillating back and forth between these are reversible, these are irreversible. The enolate like straddles that line, which means if I take the enolate and mix it with an alpha beta unsaturated ketone, half of the product comes out kinetic, half of the product comes out thermodynamic. A single enolate sucks when we're looking at conjugate additions because it literally straddles that differentiation. The energy difference is just the perfect mess to destroy everything. But if that's where it ended, we wouldn't be discussing this because we just wouldn't use that chemistry. And it turns out that we can take advantage of enolate chemistry to push us towards the reversible side of it, but we need something to kind of increase the stability just a little bit more. So if we go down and look at the bottom example, this is really what we're referencing. We have the potential to form an enolate here. Okay? And if that was it, we would say this was a bad reaction. What makes this particular starting ketone for our enolate nucleophile so special is that we also have another carbonyl. Okay? And why is that a big deal? Well, I can get resonance stabilization with the red carbonyl, our standard enolate. I can also get resonance stabilization with the blue. Those two stabilizing factors together weaken the nucleophilicity of the enolate enough that now it prefers 1,4. Okay? So just a simple enolate, a mixture of 1,2 and 1,4, we don't want to touch it. But if we have two ways to stabilize that enolate, now it favors the 1,4 and we get clean reactions. Okay, so that's the big kind of piece that comes out of our enolates, is that yes, we can use them with conjugate additions, but they have to be special enolates. How special, you ask? So special they get a name. Okay, so they're named now as Michael reactions. The Michael reaction is just an enolate reacting with an alpha beta unsaturated carbonyl. But I just said an enolate reacting with an alpha beta unsaturated carbonyl. That was a lot of words. If I just say Michael, all of that information gets transferred along with it. Okay? And so that's the point, some aspect of the point of the naming a reaction. But if we focus on the chemistry is still just an enolate, a specially stabilized enolate reacting with an alpha beta carbonyl. So if we take a look at the boxes down below, we've got two boxes. We have our alpha beta unsaturated carbonyls, so we can see the unsaturation in all of these cases, and we can see the carbonyl. I don't see those carbonyls. Where'd they go? Remember, it doesn't have to be a carbonyl, it just has to be a polar pi bond. The nitrile, polar pi bond. That's going to be enough that we can do that same stabilizing resonance that we get two electrophilic sites. Well, what about NO2? NO2 again is, or not again, but is kind of a favorite I've seen among tests because we throw in that thing and we just assume people know it. If we actually draw out the Lewis structure, that NO2 is exceptionally electron withdrawing. We actually have kind of that polar pi bond right there in that oxygen. It's an awesome alpha beta unsaturated carbonyl type. Okay, again, that is such a mouthful that we can go through and we'll introduce the name associated with these. Michael acceptors. Why acceptors? Because they're acting as the electrophile. Okay. When it comes to these named reactions, just for the record, when it comes to exams, I care about structural interpretations. I don't care about names. If you want to become an organic chemist, that's really awesome, and I applaud you for doing so. To do that, for whatever reason, currently in the field, there's a big push for people to be able to spew out names and memorize things. It's a badge of honor. Okay, I'm apparently very unhonorable because I don't know any names. Okay, but be aware that if you're going to continue down that branch, there's kind of an expectation that you memorize names of reactions and what they mean. Not just because it shows how cool your memory is, but it also allows you to convey that information more efficiently more efficiently in speaking than if you were to draw out all the structures, okay, or name all the structures. If we move to the other side of it, we're talking about our enolates. Okay, the other half would be all of our enolates, and we'll end up putting enolates in quotes on this, and we'll see why in a second. Okay, we've got the carbonyl. There's our enolate formation, but we also have a secondary way to stabilize that, so a secondary enolate aspect. You can see it show up in each and every single one of these, except what's happening at the bottom. Again, what's happening at the bottom is you have to kind of push out to that larger structure. You do have that enolate chemistry moving through there. The Gilman isn't an enolate, but the Gilman very cleanly attacks in a 1,4 position. Okay? That 1,4 position is really what's being labeled as the Michael donor. Okay? So we're looking for some uber stabilization of a negative charge. particularly a negative carbon, that now becomes a Michael donor. Okay? The Michael acceptor would be the one that would accept the electrons from that negatively charged carbon at the 4 position for a 1,4 nucleophilic addition. Okay? Yeah, I don't think I got anything else to add on that. Okay? So if we were to go through and look, this would be an opportunity where you should go through and draw this out. If we mixed all of these things together, what would we expect as the product? So again, I'm going to suggest that you hit the pause button, space, click, do whatever you got to do, stop the video, and now we'll talk about what happens. When we go through and look at the reagents, we should be kind of keying off of things that we detect. Note, kind of unintentionally, there's a positive already there. So what we might be seeing, or sorry, a partial positive already there, should be a little bit more careful with that, is that we have our unsaturated carbonyl. Okay, our unsaturated carbonyl, if we want to get fancy with the naming, was our Michael acceptor. Well, if that's the case, I then also need to find the Michael donor on the other side of it. The Michael donor will likely be an organic compound because that's what we're referencing, but I don't see a negative charge there. Okay, well, what is the point of the sodium hydride? Sodium hydride is a nice, stupid, strong base. Okay? That stupid, strong base will activate this structure to get us to the actual Michael donor with the negative charge in the middle. Okay? Interesting question that could come out of this. Sodium hydride was a stupid strong base, so it should attack in a kinetic type fashion. The kinetic type fashion should be on the outside. Why are we hitting the middle? Okay, that would be a good question for Piazza if you happen to can't figure that out, or you think you've got the answer. Go ahead and post it into Piazza and we'll talk about it. Now that we have our Michael donor can react with our Michael acceptor, long distance arrow. Okay, this causes the pi bond to shift the resulting structure, 1, 2, 3, triple. And now we've got to be a little bit careful with making sure we don't lose any atoms. Note that when I go through and do it, I'm trying to draw it in as simple alignment as possible. That simple alignment means I'm not changing orientations. I'm not trying to make it look pretty for a multiple choice exam. What I'm trying to do is make sure I get it drawn correctly. Okay? And that can be very challenging to do. This reaction, the electrons come back down. These electrons kick out towards our solvent, okay, which could be in an implied workup that isn't there, okay, or isn't specified. So we'll be picking up hydrogen from somewhere. It could be our ethanol, or it actually wouldn't be ethanol with sodium hydride, but we're going to get that H from somewhere. Okay? The exact location isn't a big deal as far as this mechanism goes. We could then draw our final answer, triple bond, nitrogen, down, 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 carbonyl, and there we go. And we've now done a Michael addition. That Michael addition is straddling right there. Okay, that was the new bond. If we wanted to go through and make this look prettier, say for a multiple choice exam, find that longest carbon chain, 1, 2, 3, 4, 5, 6. 2, 4, 6. I drew that insanely tiny. 2. Helps if you count right. There's 7 carbons. The 6, we've got that. At the third position, 1, 2, 3, I have my triple bond nitrogen. At 4, 1, 2, 3, 4, I have a methyl, and there we would have an acceptable answer that could show up in the multiple choice. Okay? And what we've now looked at is a 1,4 conjugate addition, aka a Michael addition. Okay, just kind of neat, cool. Okay, with that, we might. Oh, my computer's a little dragging, so let's go ahead and just advance. This, I told you the enamine was going to come back. this is where it comes back. How should the enamine react? So first off, we need to get the enamine. That enamine is being specified here in this upper right-hand corner. We would take a secondary amine to our groups, and we would react that with our carbonyl. Okay? If we were to go through and draw that, remember the nitrogen, we could just kind of use a cheat and say it does a full-on replace. Then we'd have a positive charge on the nitrogen. Nitrogen doesn't want to be positive. So what does it do? Pulls a hydrogen from a neighboring carbon, kicks out, and we would get our enamine. R. Our nucleophilic carbon being here when the lone pair electrons move down and there. Okay? So that carbon, okay, that is effectively an enolate. Okay? That same position is reactive up there. Okay? How should that act? Well, the enolate acted as a mix. It did both. The nitrogen structure prefers a 1,4. So we don't have to make it a fancy Michael donor or have it be a Michael donor to get the 1,4 addition. The enamine itself will already drive to the 1,4. Why? It's more stable. Okay? We're looking at that internal double bond. Everything's great and happy within it. Okay? So it drives really for the 1,4. This is one of the reasons why you'll see the enamine pop up in a lot of these conjugate addition reactions, because the enamine reacts more efficiently than the enolate in the conjugate addition reactions. So it is often used. The other thing that's nice with it is you can then remove the enamine by reacting it with water, okay, to take you back to the carbonyl. So you can still maintain that carbonyl structure. The next really cool bonus that comes with the enamine has to do with the symmetry of the structure, which is what's going on down below. Okay? If we were to look at an asymmetric ketone, and we were going to go through and try and form our enolate, well, we'd have to be a little bit more careful about the bases we used. Because if we use one base, we could get the thermodynamic. If we used a different base, we could get the kinetic. Okay? So there were two possibilities. If I want the kinetic product, I then also have to use a really, really strong base, and that could cause other side reactions. Okay? So the asymmetric enols kind of mess with our synthesis. Enamines are a little bit different. An enamine, note we've got our enamine drawn over here, will only form the kinetic. The thermodynamic actually won't form. It doesn't matter what base I use, I only get the kinetic. And that's kind of a neat observation. So the enolate has this potential for side reactions, and I have to make it more active so that it actually does a 1,4 addition. And then I also have to worry about thermodynamic or kinetic. So the enolate has all these kind of complications behind the conjugate addition. The enamine cleans up a lot of that. Okay? The enamine makes the 1,4 very clean and preferential, and it favors the kinetic in deference to the thermodynamic, which is kind of nice. Okay? I don't have to worry about that secondary chemistry. But of course, it's not just the fact. I'm also going to want to know why. Why is the kinetic formed but not the thermodynamic, regardless of the base? Well, if the base changes and we still get the kinetic, it has to be something other than base strength that's contributing to this. And it is. Okay? And really, I've framed the question in a misleading way. I've framed it looking at why is the kinetic formed. The question is actually better asked. Why is the thermodynamic not formed? Okay? That really helpful to pull out a model kit. And if you pull out a model kit, what you'll notice is the proximity between the hydrogens located at that carbon and the hydrogens located at that carbon are very close. So close that they sterically bump into each other. That steric repulsion prevents the formation of the pi bond in this location. Okay? So there's a steric negation, I don't know what to call it, a steric effect that cancels the thermodynamic formation. Okay? And that's really, really, really neat. Okay? And that's actually taken advantage of if we were to say look at an anti-cancer drug, Taxol. One of the syntheses started with a compound. Dang, I just completely blanked on the name of it. So I can't remember it. But we used to do a synthesis in lab to make that starting compound, and it goes through chemistry like this. Okay? And we use an enamine. That chemistry is sort of elaborated on, but not so much. So how do we use the enamine? Well, step one, you make it. Now I have an enamine. Now I can go through and run the 1,4. Okay? So step one, make the enamine. Step two, use the enamine to do a 1,4 reaction. Step three, eject the enamine by reacting with water. Okay? So you get those 3 steps. Remember how we talked about protecting groups being a bit weird? The enamine is kind of a similar issue, because if we look, really what we're trying to do is this reaction right here. And theoretically, I could do that in 1 step, except the energetics of that don't give me a very high yield. So I'm kind of forced to use this extra enamine chemistry, which isn't very green or efficient, because I'm using a molecule to then only get rid of the molecule. And that generates a lot of waste and a lot of expense. But if that balances out with your yield losses, sometimes you got to take one for the team. Okay? Conjugate additions, here we go. Okay? This is a challenging question because you need to think about this in the reverse. I want to know the reagents necessary to synthesize this molecule. Because I'm kind of curious where we are, I just want to hit next just to see how much more we've got. We want to know the reagents necessary to synthesize this molecule. And if we're thinking are Michael or conjugate additions with this particular reaction, of course the connection's lost, we have to try and find which bond was the one that was made. So first and foremost, our Michael donor, we're looking at the alpha position to a carbonyl. So I could make this my alpha donor, okay, donating the electrons, which would then mean this would need to be my alpha acceptor, or sorry, my Michael acceptor, and that would be the bond I'm making in between. Okay? That is a possibility. Another possibility, this is my alpha position. If that's the alpha position, then this would need to be my alpha or my Michael acceptor, and this would be the bond I would make. Okay? So what you should be able to do is to try to split it with both of those options and see if one option makes more sense than the other. Right? And yes, it's true, there is a particular answer, but we've got 2 options. We could consider it option B. Oh, and I think color coding this isn't going to work out well. Okay, so we'll call it donor, donor. This works out nicely. That has to be an acceptor anyway, we slice it. Okay, or option A. Yeah, we're already stuck there. So there's 2 different pathways we could go through to make this molecule. You should test both, decide which one's the more efficient one. Again, another opportunity to post to Piazza and see how you're reasoning through that. Last thing we'll mention, another named reaction, which again, not a fan of named reactions, but this one is kind of neat because of how much is stacked into it. Okay? This is the structure, by the way, that I was talking about, the precursor to an anti-cancer drug. This molecule right here is a molecule that starts the synthesis for a famous anti-cancer drug, Taxol, That particular synthesis, if you're looking for it, I think is Danishevsky's. Oh my goodness. I have no idea how to spell Danishevsky. I'm back to names. I did a horrible job on that. I'm going to try and erase that and pretend that never happened. But this can be done in one pot, where you take these two things, you mix them together, and you let them run for a while. In that process, first the reagents will go through and do a Michael addition, and then they will also undergo an aldol condensation. Because all of that chemistry is happening in one reaction pot, that's why Robinson gets to attach a name to it, because all of that came together in one pot. That's kind of cool. Okay, so if we tried to break that down into those individual parts, let's see what we can come up with. We have the potential for that strong negative there, again with the base. That can attack our process. We can move out. We're going to draw our product of that. There's the methyl. Let's undo that. This is where color coding can really come in handy, particularly if you're working on an exam, making sure you didn't lose carbons. Okay, and of course it helps if we have that. That electrons would come back down, pick up a hydrogen from the environment. Ta-da, there's our system. Okay, again, brutally shortened mechanism. Okay, now what can happen? I know we have the name here. Well, let's avoid the name for the moment and recognize that we're in a sodium hydroxide solution. Sodium hydroxide is a strong base. Are there alpha hydrogens? If there are alpha hydrogens, what happens if I remove that alpha hydrogen? Okay, so to give you an idea, alpha hydrogen, alpha hydrogen, alpha hydrogen. What you should go through and do is make a nucleophile that represents the blue alpha hydrogen. Make a nucleophile that represents the purple alpha hydrogen. Make a nucleophile that represents the red alpha hydrogen. And then initiate the next sequence. Okay, what is the next sequence? Those X's equal nucleophiles. Well, where are the electrophiles? Electrophile, electrophile, and running out of colors. Definitely running out of colors. We'll go with this kind of pinky color. Electrophile. So there's three nucleophiles, three electrophiles. How they connect, which ones connect, is going to be dependent for our aldol condensation. As you can see in the product, the connection is going to happen between the red one and the orange one. So let's go ahead and walk through that one. You should be able to test each of the other ones and be like, that's why that one didn't form. Okay? So why would this one form? So the first step of that connection is that we would remove our alpha hydrogen and we'd have the negative charge. That alpha hydrogen is acidic due to resonance with that carbonyl. That's our enolate. That can then attack the electrophile there. Carbonyl, ding, 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 ding. I drew that super ugly, but that's right. There's the negative on our oxygen. And there's that carbonyl still. We've now done the aldol equivalent. Okay, this would be our ketol, if you wanted to call it that. Okay, do we still have alpha hydrogens? Yes. So what can happen is I can remove a second alpha hydrogen to make that negative. I can protonate that negative oxygen. My electrons can swing down, kick out the leaving group. The end result, methyl, matches. Okay? So because there's so much chemistry stacking through that, that's why Robinson gets to attach his name. You throw a whole bunch of stuff together and you're able to predict how many different sequences of chemical reactions happen. Yes, you do get to attach your name to it, whether or not we like it or not, right? Because that's pretty cool. It did do a lot of really neat things, right? Here we've got a last test. You want to go through and provide the reagents necessary to complete the following synthesis. So we're starting at the far left. I want you to provide some reagents to go from there to the middle part, and then more reagents to go from there to the last. Okay. I am not saying that this happens in 2 steps. Right? I'm just saying that those are some big call outs to help direct you through this potential synthesis. So find where those pieces are, figure out what pieces need to be brought in, what things are missing. The order in which you do them becomes of critical importance. To help with that, I will throw in one more thing. We can go through and highlight where those structures are. So we know this entire piece is new. Okay. So this piece has to come into play. We're making a new connection between them. And then if we continue through, there's that piece. We're adding 2 new pieces. We're getting this one new to that second sequence, and because pink is what I've got right now. And this pink is new. Back here, the blue is new. The bonds that are forming are in purple. Okay? Not saying that's easy, but I'm at least setting that up so you can try and color code and piece those things out. With that, we are done, I think, entirely with chapter 18, and we're now left with just yet another synthesis chapter on chapter 19, and we'll prove that just real quickly. Ta-da! So I think that means 2 more videos left for you, and we're done with this unit.